join, but asked us to make sure we record. And he says hi to Vlad and Christian and everyone else in the call. So, hi everyone. I hope you're having a good start of the week. It's already Tuesday, and we're here for our third session on generative AI. I hope this will become a tradition in CreaTech. Today we'll focus on large language models, and of course our presenters will be the same colleagues as for the last two sessions, Cristian Bereanu and Vlad Enia. So I will hand over to them. Good luck, guys.
Thank you.
Thank you. Once again, hello everyone. Very happy to have you here. Today I have a new and exciting presentation for you. Like Radu said, it is focused on LLMs and a bit what happens under the hood. My name is Vlad. I am part of the SAP GDM team from Iași office, and together with Cristi, we'll talk to you about what we think is important to know as a first deep dive into LLMs. So please let me know if there are any problems or technical problems in sharing or in hearing me. I will share my screen now, and I will start the presentation. Okay, I hope everyone sees my screen. So let's start with an overview for today. We will first have a small revision of neural networks, what we talked about in our last presentation. Then I will present some NLP or natural language processing architecture, how they evolved over time to become BERT, which is basically the first LLM which was developed by Google, and what we have today as GPT, which is one of, if not the most popular and used LLM solution in today's world from OpenAI. Then we'll talk about a bit about OpenAI and their models, some API call references, about DeepSeek and what all the fuss is all about, and about Gemini, and the chapter regarding prompt engineering was moved to the next session in order to balance the knowledge base. And because I need some knowledge that will be presented in the next session in order to make the prompt engineering chapter as comprehensive as possible. Okay, so let's continue with our quick revision of neural networks. I picked up some of the most important things to remember from our last presentations. So this slide tells us about everything that we basically need to know about neural networks, how they train and how they function. From left to right, we have a passing, it's called forward pass or feed forward step, which is basically the network providing the prediction for a given input. So if we have two inputs, X and Y, each input is then multiplied to a given weight and by W1 and W2, which are basically what the network learns, what is modified or what is learned by the network in order to give new prediction. These products are summed and a bias is added. After that, we apply activation function in order to introduce nonlinearity in our network. And the output, together with a correct label, is fed to a loss function in order to compute the loss or the error, which is then used to basically train the network. And we propagate this error back into the network in order to adjust the weights and in order for the network to learn. I'm curious if you can see my pointer on the screen. This would help a bit. If not,
yes, it's of course visible.
Okay, thank you very much. Okay, let's continue. We talked about activation functions. The most important thing to remember that ReLU is the most popular activation. It is simple and fast. Sigma 8 is good for binary classification, and if you need your outputs to be between 0 and 1. And softmax is very good for multi-class classification because it converts the outputs of the network into a probability. We talked about loss functions and how they quantify the error of the network. If we were to have two inputs, one for X and one for Z-axis, and on the end of the third Y-axis, we will have values for the loss function. We can visualize it as a loss landscape, is what we call here in this graphical representation. When we initialize our weights, we can be whenever in any other place on this map, we can be at the top where the error is maximum. And our goal to train the network is to basically navigate this landscape in order to reach the global minimum where the error is the lowest and the accuracy is maximum. We talked about mini batch training. So instead of processing each individual element from the input dataset, we split the whole dataset into smaller chunks and we process them as a whole. This helps to remove or to hide a bit the outliers or the big errors in the input dataset that may throw off the network. The gradient is what we used for training in most of the part. What is the gradient? It is another name for the first derivative of the function, and the first derivative of a function gives us the slope of the tangent in the graph of the function. Basically, it tells us the direction of the greatest increase. So because we want to minimize the error, we use this gradient in order to go in the opposite direction, so the direction of the greatest decrease, in order to reach the global minimum of the error function. Some of the problems when using the gradient happens when we have very deep networks. And so we start propagating the error from the end of the network to the first layers. And the vanishing gradient problems occurs when going layer by layer to the input layer, the gradient becomes smaller and smaller, and the first layers don't learn as fast as the last layers, but there are solutions to that. One other concept I want to remind you about is overfitting, which is describe the situation in which a model performs well on the training data, but is unable to perform well on new unseen data. It's basically, it has become too accustomed to the training data, it is unable to generalize. And some of the neural network types that we will discuss about today, we talked about in our presentation about feed-forward neural networks. They are the simplest kind. They are good for classification or regression and also for didactic reasons. We will talk about recurrent neural networks, which are the foundation of natural language processing, and they are also used a lot in time series analysis and other sequence-based inputs. Long short-term memory networks are a step up from the recurrent neural networks and are used extensively in NLP as well. And transformer networks are the state-of-the-art foundation of LLMs that we have today. Okay. So let's talk about natural language processing and classifying text. I will present you some concepts and some important architectures to remember. So first things first, machine learning models only accept numbers as input. So our first step when we want to process text is to encode this text into a numerical format. Now, one approach, we might call a naive approach, is to use one-hot encodings. How does this work? Let's say we have the sentence, "The cat sat on the mat." And the vocabulary of this sentence which is basically the set of unique words of the sentence, is cat, mat, on, sat, and the. So if we want to encode this vocabulary, well, basically we want to encode the whole sentence. For each word, we would assign a vector with the size of the vocabulary with 0 values, and we put one on the index that corresponds to the word that we want to encode and to the place in the vocabulary. So if you look here on the right, on the columns we had the vocabulary, and for the rows we have each word in our sentence. So we have the first word, we have one on the last position because the word the is on the last position in the vocabulary. Now, if you want to encode the whole sentence, we just concatenate these vectors, but there is a very big downside. As you may have noticed, it is very memory inefficient because this is a sparse representation. We only have some ones and the rest are 0 values. We might use integer encoding, which instead of using vectors with 1s and 0, we assign an integer index to each word. The downside to that is that the encoding is arbitrary, so it does not capture any relationship between words. And if we process words individually, we just train the network to classify words, but we don't have any processing of sentences or meanings. So what we use, what is industry standard for today, are word embeddings. They are dense representations, so there are vectors with dense values, and their purpose is to give a similar representation to similar words or words with similar meanings. These values are floating point, and they are trainable parameters, just like weights in a neural network. If you have larger data sets, you need larger vector lengths, which can give more fine-grained relationship between the words, but they are harder to process. And if we want to encode the whole sentence or a sequence of words, we just have a sequence of vectors, just like for the one-hot encoding. Now, how do we actually classify text? Let's think about neural networks, because this is what we talked about until now. We have a sentence, we encode each word with an integer value, and after that, this integer value is transformed in an embedding, or we can do embedding directly on the word. There are different packages or networks that do embedding without even having to do encoding with index from the vocabulary. These resulted word vectors are then flattened, are basically concatenated, and this whole sequence of vectors is then fed to a neural network. Now, the problem with this approach is, first, we flatten the word embeddings, so it is not a sequence anymore. We do not have an order of words anymore, or if we keep the order, it still doesn't count, because the neural network will just process each word individually and cannot really capture the meaning behind words. Even though the embeddings have that meaning, the network doesn't capture that, because it takes each word individually and process it. And whatever the order we give, we will have the same result. So we want a network that can implement some kind of memory, such that it remembers previous words and then it processes the current word based on what we have in the past. So this is why recurrent neural networks were invented. We still use word embeddings, but we don't need to flatten anymore, because as an input to a neural network, which is right here, this small circle represents a whole neural network, or a whole recurrent neural network that processes each word at a given time step. And at a given time step, we'll also have as input the previous output of the neural network. So first we have the first word. At the second word, we have the output from the previous time step and the current word. And this is what the output looks like. If you were to visualize and compare neural networks compared to recurrent neural networks, we have this classic representation of a neural network, and the recurrent neural network basically have they also point in the backwards direction in order to create a recurrence, just like a recurrent function. One step above these recurrent networks is the long short-term memory, or LSTM, encoder-decoder architecture. We still embed the vectors of the words. Of course, we need embedding vectors. We will have a network that is called the encoder here, which will output an encoded phrase. This encoded phrase is called the context vector. It is fixed size, so whatever the size of the input sequence is, the output of the encoder is the same size. And this output of the encoder basically summarizes the whole input sequence. This input sequence, after it is done, it is then fed to the decoder, which will give us step by step, word by word, the most probable word that the output requires. So if we have a closer look at the architecture, we have here the encoder. Just like a recurrent neural network, we process each word in individual, but we keep the output of the previous time step. So at time step 1, we have the start embedding. At time step 2, we have the first word and the output from the previous time step, and so on and so forth until the end. This will give us the context vector here, which is fixed size, which we give as input to the decoder. The decoder and the encoder architecture are similar, but we do not use the outputs of the encoder, we just use the internal state or the context vector. This context vector is set as an input for the internal state of the decoder, and the decoder will output each word individually. And of course, we use this word as input for the next time step. This is how we do inference, or how we do prediction using this architecture. And this is how we do training. So instead of giving the previous decoded word as input in the current step, we give the correct word in order for the network to learn how to actually predict correctly. This method is called teacher forcing in natural language processing. So why do we use LSTM? Because they help with the vanishing gradient problem, making it possible to encode and extract meaning from longer sequences compared to recurrent neural networks. Now, step up for this LSTM architecture is to use attention. So attention is basically like a spotlight in which to point in our input sequence what has the most important meaning. So instead of having a fixed size output from a single fixed size output from the encoder, like we have here, this is similar to what we had before in the LSTM. The LSTM with attention at each time step will give the context vector, and which is accompanied by a set of weights. In order to give for each part in the context vector, which is the most important part on which the decoder to focus. So after each time step, the context vector is outputted, then it is fed directly to the decoder, and it gives the first word. Then we go to the next word, encoded, context vector, decoder. And just like that, we have this attention mechanism explained in a simple term. Now, if we were to have an analogy for LSTM, we can think of the encoder as a person reading a whole book, and then it summarizes the whole book in a single summary. And then the decoder takes that single summary and it generates notes however it thinks it's best. Now, if we have LSTM with attention, the encoder will not have a single summary, but will have summary notes, and then the decoder will take each note and then improve it with his knowledge. This is an example where attention is very important. So if we have these two sentences, the only difference between them is the last word. So I poured water from the bottle into the cup until it was full, and then I poured water from the bottle into the cup until it was empty. Because we changed a single word in the sentence, the word it refers to different things. So in the first sentence, the word it refers to the cup, and in the second, it refers to bottle. So this is an example where attention can help a neural network to improve and extract knowledge from text. Now, transformers are a step above LSTMs. They use what is called multi-head attention, which allows the network to process text sequences in parallel, making it much faster than LSTMs because GPUs can take advantage of this parallel processing because this is what they are good for. This parallel processing also makes it easier and more stable to scalability, but because we do not have sequences anymore because they are processed in parallel, we need something to tell us where the word is positioned in the input sequence. So we use positional encodings together with the word embeddings, and this decoupling actually helps the network to learn longer relationships. So relationships between words that are not really neighbors in the input sequence. And transformers are the foundation of LLMs like GPT or BERT. Okay, now a fun fact about Google Translate, that Google Translate switched in 2016 to a LSTM architecture, and then in 2020 it switched to a transformer architecture. Google BERT is the first LLM to be recognized. It is built only on the encoder part of the original transformer architecture because the transformer also uses an encoder-decoder architecture, just like LSTM. One interesting thing about Google BERT is that it is able to process text in a bidirectional manner, so from left to right and also from right to left. And this it does this simultaneously, and it helps with capturing context from both sides of a word. So the previous and the next word, context between those. It is trained more than mostly on masked language modeling, which it's given a set of words. Some of them are hidden, and the network has to predict what those hidden words are. And also using next sentence prediction, similar to masked word prediction, but at a level with sentences. Of course, just like any other LLM, the pre-training is done on a lot of text, and then it can be fine-tuned for specific tasks like sentiment classification, question answering, sentiment analysis, translation, whatever. The most interesting thing to remember about Google BERT is that it was the first LLM it processed text in a bidirectional manner. GPT is built on the decoder part of the transformer architecture. It is what is called an autoregressive language model because it is basically a next word or a next token predictor. So at each step, the model sees the existing sequence and it tries to guess the next word. This is why GPT is not really capable, or more, the classic GPT model and not the reasoning ones, because those are separate. The classic GPT models are not really capable of reasoning, doing mathematics or things like that. If you ask GPT to do mathematics, something in maths, it will use some external functions and external architecture in order to compute what you ask it to do. So GPTs are basically next word predictors and nothing much, but they are trained on a very large data set, so they can give the impression of reasoning or thinking or context awareness. Unlike Google BERT, GPT is unidirectional. Because it is unidirectional, it is better for generative tasks like story generation or text completion. BERT, because it is designed to analyze text in a bidirectional manner, it is better for analysis tasks. We will see that in a future slide. Just like Google BERT, it is pre-trained and then can be fine-tuned to do specific tasks. So what is the difference between them? GPT is based on the decoder, BERT is based on the encoder. One is unidirectional, one is bidirectional. And one is better for language understanding and the other for text generation. If we look at specific tasks like story writing, autocomplete, summarization, or a chatbot, chat in general, GPT is better. But if we look at tasks like sentiment analysis or spam detection, logical inference, identifying things in the text, like basically text analysis, BERT is was a better solution because BERT was replaced by Google Bard and then Google Gemini. Now, let's talk a bit about GPT temperature. I don't know if you've heard about this parameter for GPT, but I think you notice that when you ask GPT the same question again and again, you will receive different answers. And this is one of the problems for many people would like the same deterministic answer from an LLM, but this is not how LLM works. So this is what temperature is for. It's a parameter that controls the randomness of GPT models. It basically determines how confident or creative the model should be. So if we have a lower temperature, it will be more deterministic, but it is not 100% deterministic. So the lowest temperature cannot guarantee that we have exactly the same answer over and over again. But it is a bit more predictable and focused. And it is better for more factual tasks, repetitive factual tasks, like code generation, translation, things like that. If we were to use a high temperature, then we will get a more diverse and creative response. It encourages the network because it is a next word predictor. It encourages the network to predict more unpredictable words, basically. And it is good for tasks that require creativity, like storytelling, brainstorming, things like that. So if we use smallest temperature, in this example where we want a GPT to complete the sentence every good, this is the most probable result is every good thing must come to an end. And this is how the results for each word after having the sequence at one point and you want to predict the next word. These are the results and GPT picks the word with the biggest probability. If we were to give a higher temperature, then GPT will have a tendency to pick words with lower probability. So it will not give what we expect it to give, like instead of every good thing must come to an end, it says that every good thing has its price. Yeah, whatever. Okay. Now, We've seen how GPT models work. Let's have an overview on OpenAI. These are the most important chat models from OpenAI, with GPT-1 that appeared in 2018 with 117 million parameters. So basically 117 million weights. If you remember what we discussed about neural networks, how the weights are between the layers. So an immense network that was trained on 5 gigabytes of text, which is a lot. It has a context window of 500 tokens. So around 400 to 500 words, something like that. Not every single word corresponds to a single token. You also have punctuation, which also gives token, and things like that. The word don't, for example, is not a single token. It is considered to be 2 or 3 tokens because you have the words do not between them. And it was used for basic text generation. GPT-2 scaled to 1.5 billion parameters, trained on 40 gigabytes of text, 1024 tokens. It introduced zero-shot learning, which is the ability of a model to perform tasks without being specifically trained for that task. So it was better at doing new tasks and make new prediction. But this zero-shot learning also introduced a lot of hallucination. And if you remember about GPT, there were a lot of stories about how it would hallucinate about Albert Einstein or things like that. GPT-3 scaled to 175 billion parameters, a larger context window, and introduced few-shot learning, which is a more refined version of zero-shot learning. So it was also trained for specific tasks, but not a lot of examples. And it was able to be a bit more accurate, give the impression of a better reasoning, and it was more fine-tuned for conversation, and it reduced hallucination by a lot. ChatGPT or GPT 3.5, similar architecture to GPT-3, but it was more fine-tuned for conversation because it also introduced reinforcement learning by human factor. This is what LHF means here. When you talk to ChatGPT, based on the answer that you as a human give, that answer is also used as training. Reinforcement learning is basically a type of unsupervised training that is done by rewards. So the output gives the network gives an output, and then it is evaluated by a reward, either positive or negative, and the network learns by that. So GPT 3.5 or ChatGPT was more fine-tuned because it introduced the human factor in training, and it also reduced hallucination and added support for more languages. GPT-4 estimated to have 1.8 trillion parameters, but it was not fully disclosed. A very, very large context window of 32,000 words. Basically, the most important thing about GPT-4 is that it introduced multimodal support, which is basically the ability for the network to ingest more types of data, so text and image in the case of GPT-4, and also a very, very large context window. And GPT-4o, with an undisclosed number of parameters, probably several trillion parameters. Also, it was trained on multimodal data sets, so not only one text. It is the state-of-the-art model for now. GPT 4.5 is the next big thing to come out, but it is still experimental. And one important thing about GPT-4o is that it is smarter, better at reasoning, and so forth. very large context window, and it is optimized for efficiency and cost. So it is very much easier to adapt in your projects. The current GPT models used today, with GPT 4.5 being the most capable one, they all have the same context window, and the output capacity. GPT 4 Turbo is a bit too old to use today, and it's too expensive. Here is the price when you use the API. So when you use the ChatGPT on the site, you might notice that for some time you can use GPT 4.0, and after that it switches you to GPT 4.0 mini, because basically it was like a free trial on GPT 4.0. When you use the API, you pay for what you use for GPT. And the price is usually given per 1 million tokens. And these are the prices for the input and output. And there are also some prices for caching and things like that. You can see that GPT-4 mini is considerably cheaper than GPT 4.0. And for most of the tasks, GPT-4 mini is good enough. If you don't need complex reasoning, or if you don't have very large complex data. And it is also considerably faster than GPT 4.0 because it is much smaller. And we also have reasoning models. We will talk about more about reasoning models in our future session. These are very different models which are capable of reasoning, give explanation for their answer, and things like that. One thing I forgot to mention is that all of the current GPT models, except for the GPT 4.5 for now, they only accept text and images as input, and they only give output as text. For image generation, there are different modules which I will not talk about in these presentations, like DALL-E from OpenAI, and the Gemini models from Google also support image output. Okay. This is the simplest example of generating text with the chat completions API. This is the industry standard API from OpenAI. One thing to remember about this API is that it is stateless, so it does not remember. It does not really remember the chat history or the context. You have to give that yourself. So you have to keep the state of the chat on your own machine, and then at each request, you have to send the whole chat back to the LLM in order for it to have a memory or context. Now, OpenAI also released what is called Response API. It is recently released. We will talk about that in our next presentation in the more advanced features. So here is an example of Python code, because I hope you got used to Python by now. It's very simple. You just have to import the OpenAI package, create a client using an API key, and I will show you how to create an API key in our demo after the presentation. And you give the messages with a specified role and the content, which is basically the prompt. And you access the response like this, which is not the prettiest way to do it, but the new response API is better. And you'll see that Google Gemini, it looks much better in the code. You can use, you can predict, you can get the responses asynchronously as well. And you can also stream them. I will show you in the demo how streaming looks like. If you remember, when you use the ChatGPT interface, you don't get the whole answer, you get it word by word. So this is what streaming is. It's just for looking better in the UI. And you can also specify the temperature and also how you want the output to look like. So first you have to give an example in the prompt if you want the output to be specific. And if you only want the JSON and nothing else from the network, you can specify the type of the response to be like JSON or other structured outputs. You can also submit images to GPT, but you have first to encode them into bytes. I will show you in the demo how to do that using Python as well. Now, DeepSeek, which was created a lot of fuss, it was released on 10th of January, and by 27th of January, it was the most downloaded free app on the iOS App Store in the US. It caused a very big crash in the US stock market. For example, NVIDIA dropped by 600 billion in just one day. If you don't know, NVIDIA is the main supplier of GPUs used for any type of deep learning. It has basically a monopoly in this part. DeepSeek V3, which is the chat model from DeepSeek, they claim that it only cost $5.5 million to train in 55 days or something like that, compared to GPT-4o, which has similar performance and cost more than 100 million. Now, this is just a claimed value. It is often called into question by experts, and many of them believe that it is not the true cost of training because they didn't take into account like repeated training cycles. I mean, this might be the cost for just one training cycle, but you have several training cycles. It also costs money to procure hardware and also data. So this is just the training cost. It is more than likely not the true cost of training of DeepSeek V3. The reasoning model, DeepSeek R1, which is open source, this one is very interesting, that is open source, but of course it has an undisclosed training cost, matches or exceeds GPT-4o on reasoning tasks. But GPT now released specific reasoning models for that as a competition for DeepSeek. What is very nice about DeepSeek is that it is much more easier to run and operate because it uses something called sparse activation. So when you use the network, a model from DeepSeek, it does not use the whole model. Not all of the parameters are activated during inference or training, because DeepSeek uses a mixture of experts architecture. In simple words, this large model is split into smaller models, just like how you would split a monolith application into services or microservices. So each of this smaller expert network is specialized for specific application. It is fine-tuned, and they are preceded by a gating network, like a gateway, which basically determines which expert or experts to activate for each input. And this is why DeepSeek models are much more cheaper to operate. And some DeepSeek also offers, because it is open source, also offers some smaller models that can be run on local machines. And I would like to prepare that for you in the next presentation to show you how you can download and operate a DeepSeek model on your local machine. So you don't have to use API and call the model on Chinese servers. Okay. These are the specifications for the two available models. The prices are comparable to the ones for GPT, and you also have the discounted prices between 4 p.m. and 12 at midnight. Not the biggest context window, and not also the biggest output window, but it is good for competition. And I wanted to talk about it because of that the architecture of experts that is the innovation from DeepSeek. Now, DeepSeek uses the OpenAI API, so the code looks exactly the same as you would call an API model. So I will not insist on that. It has something new called fill in the middle completion, which is still in beta. You basically give a prefix and a suffix, and the model will complete the content in between. And Google Gemini, which is also not really that popular, but it should be, because compared to GPT models, all of the Google Gemini models, including the smaller one, Flashlight, the mini model, the cost-efficient model, accept also video and audio as input, compared to GPT, which only takes text and images. It has a larger context window of 1 million tokens, and the prices are somewhat smaller than GPT. Gemini 2 Pro is still experimental, so it does not have a price yet. It is not available to the public. GPT-2 Flash, it is the state-of-the-art model for now. Gemini models are better at multimodal tasks because they can also, for example, GPT-2 Flash can also output text, images, and audio. And they take videos and audio as input, as I already specified that. It is transformer based, so it's based on the whole transformer architecture, not like BERT, which was based only on the encoded part. One important thing to note about Gemini, just like I mentioned, it is better for multimodal tasks because it uses cross-modal attention, can process and abstractize information from multiple modalities, so videos and images, they can mix and match them, and they can learn relationship and dependencies between different types of data. And it can also do that for the output as well. The API for Gemini is much nicer compared to the chat completions API from OpenAI. The code looks much better. It is easier to understand. I will show the code in more detail in the demo. It also has support for streaming, just like OpenAI. For Gemini models, you do not have to encode the image into bytes separately. You just send the image as it is, and it is encoded by the model itself. And that would be it. Now, let's switch over to our demos. Just like the last time, the demos are available on a public repo that I will give the link to. We have two demos for today. One for text generation using most of the demos is focused on OpenAI. After accessing the repo, you can access the notebook, Jupyter Notebook, just like last time here, and you can open it in Google Colab by clicking this link here. You just have to copy to Drive because this is my notebook. You make your own copy so that you can play around with it. You can modify, you can run every cell and everything here separately in your own Drive, and then connect to a runtime and then start playing. Now, let's switch over to my notebook, which is already connected to a runtime, and no, this one here. Reconnect and start playing. Okay. Is the text big enough? Is it clear to see? I'll make it a bit bigger. If not, let me know. So the first step for OpenAI is creating an API key. You create an OpenAI account. You have the link here. You have to pay, like I said, every API call costs, and it is charged by token. We will mainly use GPT-4 Mini because it is cost effective, but I can show you what it cost for me to run this notebook multiple times and the next notebook as well. So I have $4 in my account here, and I can show you the usage. So yesterday and today, when I wrote the notebooks, I just spent like 5 cents, 7 cents in total. So it is very cheap. You can also use GPT-4o. It will be a bit more expensive, but I think that that $5 for starting, it is more than enough for any didactic reason. After creating the account and adding a credit balance, you create an API key. Here, I have my API key. It is secret, of course. And the best way to use API keys in Google Colab is storing them as secrets. You have the secrets here in this key tab. And you just add a new secret with the API and the name, and you access it by using these 2 lines here. You call it by the name, you give it here, and this is how you store and use API keys in Google Colab, which is very fast and very nice. So we first create an OpenAI client with this API key, and let's ask it a simple question. I, as a user, will ask the LLM, why is the sky blue? I will use GPT-4 Mini, and I will not stream this response. This is how the response looks. I just get the whole response at once, just like I would use the response is basically the same like how I would use the interface from ChatGPT. Using streaming can enrich the AI experience. So this is what streaming looks like, similar to the interface from ChatGPT. You use stream equals true, and then iterate the chunks in the response. Now, because the API is stateless, you have to give the context yourself. This is what ChatML or chat markup language is for. So this is the simple question. A simple question. I tell it that my name is Vlad, and I ask what his name is, and it doesn't have a name. It is just an assistant. But I would tell it as a system message. These system messages are like instructions for how you want the response or how you want the assistant to behave. So before asking it what its name is, I will tell it that its name is GPT. So I tell it that it is a friendly assistant named GPT. When I ask him what his name is, he greets me with my name and says that its name is GPT. And you can give whatever instructions you want in the system prompt. For example, I did something fun here, like telling it to be a sassy and sarcastic assistant, and the response matches the request, like you can call me GPT. How about sassy Oracle digital realm? It's got a ring to it, and you can repeat the request, and you will get colorful responses like that. The most amazing assistant ever. Yeah, right. Okay, so let's go back to the previous example. I tell it that its name is GPT. My name is Vlad. It remembers that, but if I ask it what my name is without telling it before, it does not remember. Even though I call the same model, because the API is stateless, it does not remember what we talked before. So you have to keep the chat history yourself. And I showed you this API, even though it is not the nicest way to use the API, because at this moment it is industry standard. So everybody uses this API. The new stateful API that OpenAI released is a bit too recent, but I think it will replace this API entirely, and we will talk about it in a previous, in the next session. So I give the chat like this. I tell it as a system prompt that it is a friendly assistant named GPT. I tell it that my name is Vlad, and I also send the response. So this is the assistant's response. This is like a chat with responses and replies. This is the reply of the assistant. So I tell it that before it greeted me by my name, and its name is GPT. And if I ask it again what my name is, it will remember from this context here. You can see your name is Vlad. Okay. Now, when you start keeping the history of the chat yourself, you add more and more tokens to your request, so it will cost more. You can use this package called TEQ token. It's from OpenAI. I will install it here very fast. And this TEQ token package can give you the number of tokens. You also specify the model that you intend to use the tokens for, and it will estimate or give you, like, not estimate, but the exact number of tokens that the message you want to use translates to. Now, OpenAI models use byte pair encoding. What you have to remember is, as a rule of thumb, generally 3 words on average translate to about 4 such tokens. Current models from OpenAI have a token window for input of 128,000 tokens, which is enough to pass like a document that it's a few hundred pages long. So it is more than enough for most tasks. But remember about this TEQ token package if you want to keep track of your tokens before sending them. Now, we can use GPT for some machine translation. I asked it here to translate from English to Serbian, this default phrase here. We can use it for sentiment analysis. So I ask it, what is the sentiment for this review? Great food, excellent service. So the sentiment is positive. And for poor customer service, we have a negative sentiment. Maybe you want to use it as a spam filter. I ask it here to evaluate this email, if it is spam or not. It is not a spam. And it also gives some reasoning of why it is not a spam. This is a spam because it sounds like a spam, because it talks about buying medication online, which is mostly illegal, and promotional language like these dollar signs here. I also instructed here as a system prompt to be a spam filter and evaluating using spam or not spam, or if it cannot evaluate, just say cannot evaluate. So this is a way that you can remove hallucinations. You can tell the model in your API that if you are unable to respond, unable to evaluate, just say that, do not invent anything else, not hallucinate. So here the response is spam for this one here. Here this email here, and I also give it some random numbers, and it said that it cannot evaluate. Oh, now it says not spam, cannot evaluate. You see how unpredictable LLMs are. I could have used zero temperature here, but I did not think about that. But this would be a good use of a smaller temperature, a spam filter. LLMs are also good for doing dirty work, work that nobody wants to do, like parsing free-form data. Here are some free-form addresses. And I ask it to give me a JSON response. I give here an example of how I want the response to look like, with name, street, city, state, country, and postal code. If there is no such value, it will leave it as empty, and it will translate abbreviations to full names, and also correct misspellings. And this is how the response looks like. It's streamed, nice. And now we can use this data structured much easier to use. You can see here, it left empty when it didn't find a state. Yeah. So just a bit of tapping into prompt engineering. The most important rules in prompt engineering is to give proper instructions, to be as detailed as possible, to give examples in order to help the LLM to give you what you expect. And now let's make use of the 128,000 context window and load a whole document into it. Here we have the Microsoft 2022 annual report, which is I think tens of pages long. I converted it into a TXT file. If you want to try that yourself, you find the file in the here on GitHub, the annual report TXT. You need to also add this file to your drive in order to use it in Google Colab. For example, I have the file path here as a secret, and then access it just like I did with the API key in order to not expose my file structure here in this public notebook. So I open the file using file.read, very simple in Python, and I tell it that please summarize this annual report from Microsoft and also use Markdown formatting in your output. And I give the whole report that I opened here. And the output looks like this because I use Markdown and also the Markdown function from Python display here in the notebook. The output is nice and structured, just like a Markdown document. Okay, let's continue with our, or maybe if you have questions, now would be a good time to ask them, or you can leave them for the end of the presentation. Okay, let's go to the next demo, and then we can also pass some questions. Okay, so the next demo is about multimodal LLMs, which take and process other types of inputs like images. In the case of Google Gemini, they can also take videos and audio. Now, just like the state-of-the-art LLMs, the smaller ones also have a possibility to process images. And we will use the smaller LLMs because they are enough for these notebooks. So, just like the document that I had for the Microsoft annual report, you can find here in the multimodal LLMs directory the images and the videos that we will use for this lab. You add them to your drive, and then you use the path here in the Colab notebook. So let's open our first image. This is an image of a cute corgi dog. And one thing to remember about OpenAI, like I said, if you want to work with images, you have to encode them in bytes. So you have this method here that returns the byte data of an image, and we will use it to pass it here. Together with the prompt, I ask it describe what you see in this image, and then I send the image as an image URL using the method described above. So let's first start by running the notebook. You need to mount to your drive account in order to use files first, and this is what I did here. Okay, we open the image, load it into memory, and then create the function, and then use it to send it to GPT-4o Mini, and it will give us the description of the image streamed very nicely. Features a corgi standing on grass, playful and happy. It describes the coat of the dog. The tongue is out, enjoying the moment, the background, the wooden structure behind it. So very much in detail. Now, OpenAI does not support video inputs, but you can bypass that by converting the video into a stream or a sequence of frames. This method does just that. Don't worry about it. You can use it as it is. This parameter here, it's basically what do you call it? The sampling rate. So how many frames you want from the video per second. So I will use 1 frame per second and have the list of frames here from the video. It is the video of the corgi dog running. Maybe I can show you in my Drive account. If you want to see, if you're curious about the video, It is the video from which the previous image was extracted. You can see a dog running to a ball, playing with a ball. Okay. Okay. So we get the list of frames and then we send them. Here I use a lambda function, but you can just use a simple for to create this content object to send each frame as a list, and then ask it to create a summary from the video. We need to give a joyful video playing in a sunny day, a grassy field, tail wagging. So very much in detail. Now let's switch over to Gemini. Google Gemini, we will still use the cost-effective solution from Google Gemini. Of course, you already have a Google account. You can get the Gemini key directly from here, from Secrets in Google Colab, by clicking here, and you click Import Key from Google AI Studio. You create a Google Studio account. You create an API key, and after you press Setup Billing for that API key, you will receive $300 of free credit from Google, which is available for 90 days. So like a free trial, you don't have to pay for Google Gemini, as opposed to OpenAI. And after doing that, if you import the key again, it will appear automatically here in your secrets list as Google API key, and you can use it directly in your Google Colab. So let's import our key and create a Gemini client using our key. We load the image just like we did before. We do not need to convert it to a byte stream because we can send the image together with the prompt in a single request. And we use generate content stream method in order to get the response as a stream. If you don't want the stream, you just use generate content and just like that. So we send the image to Gemini Flashlight, and this is the response. Similar to GPT's response, you can use it for object detection. So I ask it here to return a bounding box for the dog using a JSON format for the box corners. And I specify the format for me to be easier to draw the box on the image. I ask it to use JSON only, and I also configure the model here to use a structured output. You remember you can do that with OpenAI as well. So this is the output. I send the image and this prompt. This is the output, and I use some code to draw the image here, and this is the bounding box that it was generated. Let's see, sometimes it is out of shape, but most of the time, let's see a different bounding box. Most of the time, it surrounds the dog like you expect. Now, you can also send videos to Google Gemini. You don't have to process frames like we did before with OpenAI. You can use the files API from Gemini. It will extract the frames automatically for you, and it also passes the audio signal. When we extracted the frames for OpenAI, we just have the frames. We don't have the audio signal anymore. Now, if the files API will extract the images at 1 FPS and audio at 1 kilobyte per second for yourself. So you load I have the path here as a secret in my secrets list. And I just call clients files upload, and that's it. Specify the path. It uploads the file. Here I can use this while loop to check the state of the file. If the upload is done, if not, tell me when it's done, and if it's failed here. So the video is loaded into the file API. You can read more about the file API here in this link. I think you can store up to 20 gigabytes of files for free, and they are available for a limited time. Then they will be deleted for the free tier, I think. And you pass the video by using the files from get after the video is done uploading. You pass it together with the prompt and you get the response. The Titan is born in its mouth, appears to be enjoying a sunny day in the park. Now let's use this very confusing parking sign from somewhere in the US. I don't want to stay and read about everything here. So I will send the image to Gemini. I tell it that it's 5 p.m. on a Thursday. Am I allowed here to park? And you can see here that the Gemini will give a response. It will explain the signs, everything about the signs, and it will give the conclusion. Yes, you are allowed to park here for 30 minutes. Okay. If you're curious about how do we send chat context to Gemini models, because I told you that the API is nicer because this is stateful compared to the chat completions API from OpenAI. You just create a chat with a specified model and then send each message as you like. After sending each message, you can get the response separately, or you can get all of the response history using the chat curated history here. And that's it. The Google Gemini API is much nicer, like I said, because it is stateful. But there is also a response from OpenAI, which we will explore in future sessions. So that would be it from my part. Thank you all for the attention. If you have any questions, I'm very glad to answer them. You can message me anytime on Teams if you want to discuss, maybe ask a question, maybe I can help you with anything AI related. And me and Christy, thank you for your attention. So please, if you have questions, I'm very glad to take them. Yeah, so if you want to play around with these demos, I will send you a link to the GitHub repo, and you have the instructions there. You have the instructions there of how to run them, how to use API keys, and everything you might need. I will send you the link here in this chat, and at any time, if you have any questions, like I said, please message me. So, no questions?
It seems there are no questions for now.
Seems like I'm a good
thank you,
presenter.
Christian, for the
It
session.
seems very, very
today.
interesting. Very, very interesting, and in the same time, scary.
It is scary, and if you start looking into the API reference from OpenAI, it gets even worse because there are a lot of advanced features available. You can do a lot with LLMs today, and it is very accessible from the API. And we will talk about some of them in the future session. Like, this is just a list of what you can do with the API, assistants, and things like that. But we will talk about it in a future session, the most important and the most used things today. Yeah.
Thank you very much.
Thank you,
for the
guys.
presentation.
Thank you very much for your attention.
Thank you. Great presentation.
Thank you very much.
So meanwhile, if there are any questions, feel free to reach out to Vlad and Christian on Teams, and looking forward
Anytime.
to meet you on April 1st on our next session focusing on advanced LLM features. So thank you all for joining. Recording will be available shortly, and wish you everyone a good afternoon.
It's gonna be
Thank you
April
very much,
1st,
everyone. April 1st, yeah.
and it will not be a joke, right?
No.
It will really be there.
No.
Hopefully not. Hopefully not.
All right. Thank you.
Thank you all for your attention.
Bye-bye.
Bye.
See you. Bye.
Bye.
you.